Today we have 4 presentations on GIS and how it's used to study the plant and animal life environment and ecology. We are going to go through our presentations and hold all questions until the end. If you have questions, please do put them in the chat, and then we will go through those after all of our speakers have finished their presentations. So our first speaker this morning is Cooper Sykes. He is a sophomore Wells Scholar at Indiana University, Bloomington, pursuing degrees in environmental and sustainability studies and geography with a minor in German. His research interests include mapping environmental and human health with GIS and working on forever chemicals and persistent pollutants. Cooper is a student geospatial sciences volunteer at the U.S. Environmental Protection Agency, and he volunteers in the Heights Laboratory at the O'Neill School of Public and Environmental Affairs. Outside of his research, Cooper enjoys classical music, playing his saxophone, watching and playing sports, and eating ice cream. He is deeply honored and excited to be here today. Cooper will be speaking on the Indiana Roadkill display, the role of civic science in GIS. So let me get his poster all set to go. All right, Cooper, please take it away.
Thank you so much, Flora. I really appreciate it. I hope you all can hear me okay. If not, please let me know. And I thank you for bearing with me in this perhaps unconventional setting. I was just truthfully really excited to reserve this room to present, and I wasn't quite sure how it'd come through on a webcam. So if nothing else, it's a new, fresh look for the presentation. So as Laura said, I will be presenting on the Indiana Roadkill display, the role of civic science in GIS. And if you know, it's a Sustainability Scholars Program. This was a project I originally worked on with the Sustainability Scholars Program last semester here at IU Bloomington. And I'm really excited to be able to share some of what I did with y'all today. So can we go to the next slide, please? Fantastic. All right, so here you see a research poster. So you might be really into research posters, and if so, I encourage you to take a screenshot, look it over. However, as geospatial scientists, I thought we might enjoy looking at something perhaps a bit more geospatial. So I actually put together a story map, which might be a bit easier to follow than this very word-heavy research poster. So we could go to the next slide and go on to the story map. That would be very exciting. So we'll get there eventually. In the meantime, as we're getting the Indiana Roadkill display pulled up, and here we go. All right, so the Indiana Roadkill display. Can civic science be used to decipher patterns about Indiana's ecosystems? So can we go to the introduction section? Very exciting. Okay, so how did we get here? Why are we here? These are fantastic questions. So the automobile has had a profound impact on American life. Lots of our cities were designed around the automobile. And with the result of the automobile having a greater influence on American life, we're also seeing more and more wildlife vehicle collisions. We see around 300,000 wildlife vehicle collisions each year. And honestly, that probably could be an underestimate. Because how often when you're driving down the interstate at 70 miles per hour and see a roadkill carcass on the side of the road, how often is that being reported? The cost of these collisions is over $8 billion. And truthfully, it's something that many ecologists and many just average citizens are also noting, hey, this is perhaps a problem here with our ecosystems and in the wildlife of the world. So to gather more information about roadkill and the effect of roads on ecosystems and biodiversity, civic science has been increasingly used. So can we go on to the next part where we're talking about what is civic science? I'm glad you asked. So civic science is really employing the general public to collect and report data on critical scientific problems. So this could be everyone from retired researchers, professors, teachers, students, or even just people that work at normal day jobs. They're like, hey, let's go out and let's do some science. And there's been a lot of research on this and actually showing its positive effects. You look at South African researchers and they said, hey, the public can fulfill vital roles in roadkill studies to look at overall patterns of roadkill and high risk. And one of the things that really inspired our project was the California Roadkill Observation System. This web application really allows the users to input roadkill sightings across California. And there's an interactive map and all these summaries of data. And it is just an immaculate thing if you ever want to look up and look at a really well done roadkill GIS system. So, and we've also seen Civic Science be able to potentially increase sustainable behaviors in its participants. So we could scroll down just ever a bit. So in this project, what was our research question? What are we trying to do here? We look at all this positive data on civic science. We note the problem of roadkill are unfortunately becoming increasingly common across the United States. And we're like, can civic science provide relevant data regarding Indiana's roadkill? And our hope was that if participants could report data that is consistent and large in quantity, and we might be able to see a specific species or specific area that is at risk, we can employ further research and mitigation efforts. So how do we do this? We start by creating the Indiana Roadkill display. So we know there's going to be two parts to what we're doing here. We're going to be both developing a usable web application and trying to get enough interest from those in the community to say, hey, let's get enough data input here. So how do we create the web application? We looked at Esri's ArcGIS Pro, and that's where the original feature layer was created. This was actually the first thing I had ever worked on in ArcGIS Pro, and this was going to be something that was very public, very outward facing. So a lot of comments about usability and ideas about how to make this the most accessible were always taken into account. So we created a feature layer with different species in Indiana, exported it to ArcGIS Online. It was set to public, and then what people could do was they could edit the web application, the feature layer, via the web application. And anyone that was hoping to input a sighting could list the species, the date of observation, the date of recording, the mode of transportation they were using, and just how often they frequent the area. This gives us enough data to say, hey, like someone saw this species on this date, recorded it when they were driving, and they often go through this area. So that's a helpful array of areas, and we could use all that different data to just kind of get a sense of where are species getting killed, what species are getting killed, and when are species getting killed. So we've created this web application, but no one is using it yet because we haven't sent it anywhere. So we got to get the word out. So we could scroll down to getting the word out. So we started to try to make contact with users starting on January 19, 2021. So we contacted 14 different organizations via email. This includes the Indiana Department of Natural Resources, the DOT, and then we also contacted 26 Indiana high schools via email. So we're talking about environmental clubs, key clubs that need volunteer hours, or even just science departments that are looking for something to do. Unfortunately, we had a pretty low response rate from high schools, and organizationally, even though we had a meeting with the DNR, we never were quite able to get organizations or high schools to latch on to the Indiana Roadkill display. However, the Indiana Nature Facebook group, I guess, is it called Meta Group now? I'm not quite sure. But anywho, they have 11,000 members, and I posted about this and asked, hey, would any of you be interested in posting any roadkill sightings you have on our Indiana Roadkill display? And this is where our data collection really started to take off, as the Indiana Nature Facebook group really started to have some volunteers that were interested in acquiring this data, recording it, and consistently. So once we got this data, we then analyzed it in ArcGIS Online using tools like Find Outliers, and we're just trying to determine general patterns, areas of concern for Indiana wildlife. We're not necessarily looking at what, like overall, like, oh, this is going to be the finite place, this is where all the animals are being killed, but no, rather just, is there any general patterns? Are there any areas of concern? Can we scroll down just slightly, please? Fantastic. And additionally, an Esri story map, which we are looking at right now, was developed. And really the strength of contacting the public is we can cover a wide range and get a lot of consistent data. But there's also the struggle with how do we make this data reliable and how do we get that general interest? So those really come to the struggles that we encounter. And I will go more into that in the discussion as well. But first and foremost, let's start walking through these roadkill sightings. And as we get here, one thing I want to note is, as we're looking at this, the data that is reported, most of the numbers you will see are reported as of April 29th, 2021, as I presented this data at the Sustainability Symposium for the Sustainability Scholars Program here at IU. That was when I was doing the most work with the data. In the coming months, I haven't done as much work with the data, but you're still seeing civic scientists across the state reporting data. So you look at the points, and I'm like, oh, there's about 100 points here in Northeast Indiana, and you're like, Cooper, that's a lot more than 100 points. You're certainly right. I just haven't been able to do quite as much with that data yet, though it is still coming in. But talking about hundreds of points is not quite where we started. So these are the first 2 points of our web application. We started sending it out in January, but one researcher actually remembered that they had seen 2 deer sightings along a road near the end of December and decided to report them. So those were our first 2 sightings. And you'll kind of see the pattern of us going from a small number of sightings to a much larger number of sightings as we go along throughout the data. So then you can scroll down as we go along our sidecar. So next up, we see a possum sighting, and this was notable because the resident was walking. Oftentimes, when we associate wildlife vehicle collisions, we think we're also recording them while in vehicles, but also just on your daily walks or getting out on the town, you can actually be able to see roadkill and report it into the web application. Next one, please. All right, and then we see this one little salamander near Danville. And this, what I wanted to point out here is that it's not always possums and raccoons and deer that are being reported, but actually we also see things like salamanders or snakes or toads. So there's the little salamander right there. And we can scroll on, we actually can scroll down on the sidebar. I appreciate you scrolling in there, Laura. So later, here we see all the points. So the northern half of Indiana really started to get involved. So you've seen a couple of them, but you really start to see all these points go through. And this probably shows geographically that most of the Indiana Nature Facebook group happens to be located in northern part of Indiana. Yeah, someone did post something in Lake Michigan, most likely an outlier, but you know, maybe someone was on a boat and saw that unfortunate piece of roadkill, so never quite know. So let's scroll on down. So we're starting to see this, and let's go through this data. So on the Grand Army of the Republic Highway, we see a series of roadkill. They have raccoons and rabbits, and then we can keep scrolling on down as well. Now we see another stretch, North State Road 109 for Columbia City. We're seeing another stretch right here. You see, unfortunately, a cat and a large bird. So we're seeing a variety of species, which is very sad. And and then right here, we can stop here for a moment. This is north of Noblesville, and we see possums, raccoons, and a skunk reported on a short stretch of road. And what I really like to point out here spatially is we can start to have inferences. And while we can't necessarily confirm any of these suspicions, most likely we're starting to see people's daily commutes. Those that are interested in this web application, those that are driving to work every day, driving to school every day, and they're saying, hey, I see roadkill here, here, and here along my daily path. And that's really when you start to see things like these take off and gather interest as it becomes part of your daily routine. So those past 3 examples have really been the similar stretch of road. And while it's definitely certainly not impossible that it could be various different people, you might actually be seeing daily routines starting to come along. So we can slide down to the next slide. Even Dr. Avram Pernick, my mentor, he's the one that really helped me assist with this project. You can see he reported some squirrels near Griffey Lake in Bloomington. I just thought it'd be fun to shout them out. So thank you for looking at that. And then we can scroll down to, I believe our final summation, which is in total, the Indiana roadkill has retrieved 135 sightings across the entire state as of April 29, 2021. Checking it this morning, we're now up to 259 sightings, actually. So we're actually starting to see dozens upon dozens of input data, and we're really excited to see, and you even could look in summer months and start to see, oh, there are perhaps more amphibians or reptiles as it is the summer and a bit warmer outside. So let's go down to discussion. So far I've gone over what we were doing and shown the results that we have, all the different points. But why do we care? Why does this mean anything? So the roadkill sightings show that civic science can be useful in generating consistent reports of roadkill data. There are particular areas where it's consistent over the course of time that on certain stretches of road, you're seeing report after report of roadkill. However, we do have to take a step back here, and 135 reported sightings is a decent amount of data for a web application its first 4 months of use. After all the phone calls and talking and such, it was very exciting to be able to get those, to get enough data. Very unfortunate that the data exists, but we're happy to be mapping it. Though we can't say that we produce any conclusive findings about the overall state of roadkill in Indiana. You'd require 100 or more points over a wider area over a longer period of time to make such a conclusion. One of the key limitations here is we have an inability to validate participants' roadkill reports. A few participants did submit pictures, but truthfully, it was a separate thing. So there was a web application, and then separately, I had created a Google form saying, if you see any pictures, feel free to submit. And I believe we did not receive our first picture until like 5 months into the roadkill display. So no one can really truthfully ensure that the sightings and web application is entirely accurate. As you guys said before, if you're driving down the interstate at 70 miles per hour, listening to Taylor Swift's re-recorded Red album, you're probably not being able to be like, oh, is that a chipmunk? Is that a rat? It's very difficult to determine that. So even if we gathered all the necessary data to make conclusive findings, the findings would actually just simply be generalized to overall patterns of roadkill and saying, hey, this area might need some more attention. Let's do further research. Let's go a bit further and see if we can employ some mitigation strategies. So going through all those limitations, it is disappointing to not be able to make conclusive statements. The involvement and the energy from civic science is really what I began to harken on with this research project, as it really showed that civic science does have this potential to be an effective tool for ecologists studying roadkill and attempting to decipher general patterns. So sustainability for roadkill research really involves just creating and maintaining a system of movement for humans where wildlife vehicle collisions are just not a risk to wildlife populations as a whole. In a world already losing so many species, we've heard the reports on biodiversity and extinction. It is imperative that biodiversity isn't continuing to be threatened by highways and roads. And thankfully, civic science can really help with this because it shows community involvement, community accountability. Heather Reynolds et al. Showed that civic science can be key in generating findings about sustainability locally, allowing residents to take a greater interest in how they interact with their environment and their locality. And one thing I will note here is I wish I had done perhaps a better job of continuing to keep in contact with these Facebook users. Part of civic science is maintaining that relationship, and that's part of what I feel is a bit of a failure in my research is I should have kept up with them better and such. However, that's something that's always key to be focused on. When you're doing projects like these, it's important that you're not exploiting communities and that you're continuing to communicate. And I was proud. I shared the story map with them. I shared the continued Roadkill web application. But it's always something to keep in mind and recognize points where you failed, and points where you can be better. So overall, the Indiana Roadkill display did not necessarily generate groundbreaking conclusions about where and what species are being recorded in wildlife vehicle collisions in Indiana, but it really does just suggest that civic science research at Indiana University or elsewhere in Indiana should start to be a focal point among research discussions. We can scroll down just slightly here. And we can get to our conclusion. So overall, we're seeing over 100 roadkill sightings across Indiana in the span of about 4 months. And despite the limitation of ensuring validity, these sightings could still be used to see perhaps overall patterns in the future with an updated methodology, I should say. And while we weren't able to say, oh, this is exactly where all the roadkill are, we can employ the greatest mitigation strategies here, the Indiana Roadkill display still demonstrated that excitement from volunteers and civic scientists can create a consistent stream of data regarding roadkill sightings. And to ensure that human wildlife interactions are sustainable going forward, we should continue to employ civic science and do further research with it in order to help protect Indiana's ecosystems. So we can scroll down to my acknowledgements, but that's the end of my talk. And if you have any further questions about the terminology of civic science, the particular species that we saw, feel free to ask it in the Q&A section or session after all the presentations have been done today. So thank you so much for having me, and I can't wait to hear all the rest of the presentations. Y'all are going to do great. Thank you.
Thank you very much, Cooper. That was great. And as Cooper said, we will be holding questions to the end of all the presentations. If you have questions, please go ahead and put them in the chat. So up next, we are welcoming Dr. Sungchan Oh. He is a postdoctoral research associate in Purdue University's Geospatial Data Science Laboratory, working in collaboration with the Department of Forestry and Natural Resources. His research in sustainable forest management involves techniques for extracting stand-level forest characteristics from statewide LiDAR data. Today, Sun will be speaking on statewide canopy height model generation using USGS 3-depth LiDAR data in Indiana, USA. And I'm going to get your presentation up here in just a sec. All right. Welcome, Sun.
Hello. Okay. Hello, I'm Sungchan from Forestry and Natural Resources, Purdue University. Today, I'd like to talk about statewide canopy height model generation using USGS 3-depth LiDAR data. Next slide, please. First, canopy height model is a raster data set where each pixel value represents elevation from ground to the top of the canopy surface. So the canopy height model is a very important data set that can be used as a baseline information for forest management, but also can be used to calculate important forest metrics such as forest biomass or carbon sequestration. Next slide, please. Okay, so we're targeting to generate a statewide canopy height model with 6-meter resolution. Page 5, please. The input data is USGS 3-depth or 3D elevation program LiDAR data, which is essentially a set of XYZ points, 3D points, which has XYZ value. That's my fault, not my fault. And the USGS 3D LiDAR data is available pretty much in everywhere in United States. So if you're interested in your area where the LiDAR data looks like, you can download that from USGS sites. Can you go to the page 4, please? The characteristics of this input data, USGS 3D LiDAR, has vast spatial coverage compared to the other LiDAR data set. But the point density of LiDAR data is pretty much lower than other airborne LiDAR data sets. The point density is around 2 to 10 in general. Can you go to page 6? And I'm going to tell you how to calculate the canopy height. So the picture in the left is a point cloud data, which is 3D points. And first we do a ground and non-ground classification. From that, we get the surface of ground, and which is called in 2D raster data, it's called a digital terrain model. And every pixel area in DTM, we have a ground elevation from DTM, and we get a highest or a pixel with a highest Z value in point cloud data to calculate the distance between the ground and the top of the surface. After that, we suppress the height in the non-forest land using the land cover map. In this process, we use National Land Cover Database. Next slide, please. The original data set comes in a 1.5 kilometer by 1.5 kilometer tiles. So we had to merge these tile data into one to create countywide canopy height model. And we merged these countywide canopy height model to create statewide canopy height model. The interesting fact in this is the size of the data. The original point cloud data, the size of original point cloud data was 10 terabytes, which is 10 times 1,000 gigabytes. But when we generated statewide canopy height model, it was only 13 gigabytes. So the user can easily visualize it or use it for another spatial analysis. Next slide, please. This processing was possible thanks to the high performance computer and network storage device at Purdue. But even though we use these computing resources, it took about 60 hours for data processing. And this data is now being provided to users through a web server. I'm gonna briefly introduce the web address in later. Next slide, please. So in the process of creating the canopy height model, we created a canopy height model with different pixel size. And we figured out when the pixel size was 1.5 meter, the output canopy height model had a lot of no data points. So we had to increase the pixel size until it became 6 meter, and there were no data pixels in that data set. This is partly due to the low point density of 3D LiDAR in early 2010. Next slide, please. And we also checked the consistency of 3D canopy height model. We compared the tree height measurement in two different data collection periods. So we had a field measurement, which is a forest inventory data in 2020 and 2008 to 2020 and 2013 to 17. So the residual had 95 percentile as 4.8 meter. But when we did the same thing, which I mean, compare the canopy height model in two different time frame, it gave us 95th percentile of 3.7 meter, which was smaller. So we could say tree height obtained from canopy height model was more consistent than field measurement. Next slide, please. And we also checked the accuracy of 3D canopy height model. We compare the canopy height model based tree height and the field measured tree height. And it gave us a R square over 0.8, which says it's our canopy height model is pretty much accurate. Next slide, please. One of the possible application of using this canopy height model is change detection. When you compare these two images, especially at the lower left corner, there is a region that where a canopy height was substantially decreased, which is possibly due to human disturbance, such as harvesting or prescribed fire. Next slide, please. So we produced a very reliable statewide continuous canopy height model. And that canopy height model was reliable, accurate, and consistent. We hope that our canopy height model can be used also to evaluate other important forest metrics such as biomass and carbon. Next slide, please. This research was possible thanks to all our collaborators in Purdue and Indiana Department of Natural Resources. And you can access this data and visualization pages using this web address. Thank you for your attention, and I'll take all your questions after our presentation is finished.
Thank you very much, Sun. And yes, as Sun said, if you have any questions for him or for Cooper or our next couple of speakers, please do put them in the chat. So up next, we have Zachary T. Finn from Purdue University. Zach is a wildlife science master's student at Purdue University. He is passionate about nature restoration and has incorporated that passion into his graduate studies at Purdue. He modeled the potential for greater prairie-chicken reintroduction to Northwest Indiana and Northeast Illinois based on the area's habitat suitability. Today, Zach will be speaking on modeling the potential for greater prairie chicken reintroduction to an Indiana tallgrass prairie. So take it away, Zach, please.
Thanks, Laura. Thanks everyone for coming. So I guess we'll dive right in and ready for the next slide. Could you click once?
Sure.
All right. So why am I doing this at all? Well, as you can see through the historic range map and current range map, in the lighter colored areas is where the greater prairie chicken used to exist. And then in the darker colored areas is where they currently reside, although some spots are missing, like in southern Iowa and central Wisconsin. But there's been a sharp decline in greater prairie chicken geographic breadth in terms of its historical range. So I wanted to identify potential future locations for reintroductions. One more. So like I said, there's potential for reintroduction. Just got to identify the areas of habitat that this species could be reintroduced to. And to evaluate this question, I use species distribution modeling, and that's an umbrella term for a variety of methods for predicting species distributions. And the specific method I used was maximum entropy. It uses species locations and environmental data to estimate a distribution closest to uniform, otherwise known as maximum entropy, under the constraints of the averages of the environmental data. Moving on to my objectives, I wanted to predict greater prairie chicken habitat suitability values for Kankakee sands and the surrounding landscape. I'll talk about that in a second. Using spatial data with pixelated, binary, presence or absence, output format, and graphically displayed in a map. And I also wanted to provide logistical and operational information for the Nature Conservancy in regards to any potential future greater prairie chicken reintroduction. My prediction and hypothesis was that the majority of Kankakee sands and the surrounding habitat patches would be suitable. Suitability values greater than or equal to 0.5, my arbitrary cutoff, and to reintroduce greater prairie chicken. And this is based on the availability of thousands of hectares of habitat relative to the recommended minimum habitat of a population of greater prairie chickens in Illinois being only 610 hectares. Ready? One more. And again. All right, so my study area is a Nature Conservancy property known as Kankakee Sands. It's a not quite restored tallgrass prairie because it's set in the footprint of a lake that used to be there. So it's new tallgrass prairie, but nonetheless, it's tallgrass prairie, which is a rare habitat type and it's still valuable. So like I said, tallgrass prairie, but there was also some wetlands that has a diverse array of plant and animal life, such as they have bison on site, which is pretty neat. There are badgers, coyotes, foxes, bull snakes, plains pocket gophers, you know, your red-tailed hawks and other buteo and accipiter raptors. Next, please. And then this is the map. As you can see, it's not just Kankakee Sands. There's some surrounding habitat patches as well. I'll get to those in a second. So there's Conrad Savannah Nature Preserve, Beaver Lake Nature Preserve, Willow Slough, and others. Next, please. Next. So the surrounding landscape, Northwest Illinois, Northwest Indiana, Northeast Illinois. You know, like I said, Conrad Savannah Nature Preserve, Beaver Lake Nature Preserve, Willow Slough Fish and Wildlife Area, as well as Iroquois County State Wildlife Area. And as well, there's some smaller habitat patches, which we'll see in the next map. So the dark gray to the top right is Kankakee Sands. Top left of Kankakee Sands in the northwest, Conrad Savannah, and then Beaver Lake Nature Preserve in the northeast, Kankakee Sands. Southwest Kankakee Sands is Willow Slough Fish and Wildlife Area. To the west of that, across the border in Illinois, is Iroquois County State Wildlife Area. And then to the northwest of all of this is a smaller collection of smaller habitat patches, and it's part of a larger effort by the Illinois DNR and Illinois chapter of the Nature Conservancy to piece back together what once was a large expanse of tallgrass prairie. As for my animal data, I requested LEC location data from the natural heritage databases of Illinois, Indiana, Wisconsin, and Missouri. Why not? Why not Indiana? Because Indiana hasn't had any greater prairie chicken LEC since like the 1960s or 70s. But why am I using LEC locations, and what is a LEC? Well, a LEC is when a certain species, the males compete, they get together to compete and display to see who's the biggest and baddest male. And the dominant males will then mate with the most females. And a LEC location or LEC site is simply the place in which they perform this reproductive behavior. But why did I choose it? I chose this because LECing is, and LEC site selection is associated with other year-round natural or life history habitats, such as nest site habitat and brood rearing habitat. Why did I use all these states instead of just Indiana and Illinois, since their prairies are most likely to be the most similar to each other? There's a lack of data volume from just 1 to 2 states alone, so I had to extrapolate a little westward. And I only used data from 2010 to 2020 to try to account for land use change over time. And to ensure independence of my, or help ensure independence of my data observations, I use a spatial filter of 1.52 kilometers for the greater prairie chicken LEC sites. For my environmental data, came from all 5 states in which I was modeling out to in order to hone in on Kankakee sands and the surrounding landscape. The states were Indiana, Illinois, Iowa, Wisconsin, Missouri. Majority of my environmental data came from the Natural Resources Conservation Service Geodata Spatial Gateway. First one was cropland data layer. I nicknamed it land cover. I used this instead of the actual land cover layer because the actual land cover layer that they offer doesn't get very specific in terms of actual habitat types. Whereas in the cropland data layer, there's all those crops being listed, yes, but there's also specific habitats like grasslands and marshlands, forests, stuff like that listed. Next, I used their conservation easements areas layer to try to see if there was any sort of connection in LEC site selection and conservation easements. My other layer was the elevation data set and the 30-meter raster resolution. My next layer was a combination of the Tiger primary and secondary roads with Tiger streets. Became my roads layer, and I turned it into a density layer. From the Homeland Infrastructure Foundation level data, I obtained the power transmission line data layer, and that was again another density layer. From miscellaneous US wind turbine locations from the US wind turbine database, I converted that again into a density layer. And next was moderate resolution imaging spectroradiometer of land cover. So the cropland layer is a categorical layer, and this one is a continuous layer, which assigns numerical values to different vegetative covers based upon satellite data, which is collected in the blue to near infrared spectrum. And then finally, I created a slope layer from my elevation layer, nicknamed it slope. So all this data layer conversion happened, of course, in ArcGIS Pro, specifically creating the density layers and the slope layer using the slope tool. But further processing needed to be done in order to fit the modeling program, which requires that all layers are to the same extent and converted to the coarsest resolution, which was MODIS, which had a resolution about 232 meters. I used the same projection coordinate system, except for roads, transmission lines, and wind turbines. I use Albers equal area conic for that, and that's to ensure more accurate density measurements. For my data analysis, my specific species distribution modeling method was MaxEnt. It's a form of presence-only modeling, meaning it relies only on known presences and not expensive to collect absence data. In absence of that true absence data, it generates its own 10,000 points. Pseudo absence points is what they're called. By default, it just generates them over your entire study area of interest, but mine were custom. I only generated them within the applicable habitat types, which was grassland, and that's to minimize sampling bias. And what MaxScent does, it predicts a relative likelihood of species occurrence on a continuous or binary 0 to 1 scale. Moving on to my models, these were inspired by Hovick et al. 2015, who performed similar work evaluating habitat for greater prairie chickens in Kansas. So the first model was the universal model, incorporated all variables. Second was environmental, had all natural variables. The anthropogenic land cover model was all human-related variables with the addition of the land cover layer. And then anthropogenic modus was, again, all human-related variables, but with modus instead of land cover as the habitat variable. For my model evaluation, and MaxScent automatically generates these area under the curve scores, and AUC scores greater than 0.75 are considered useful. I also looked at the 10th percentile training presence threshold emission error rates, which is something MaxScent automatically does in order to try to account for potential errors in data entry. And then the last thing I looked at was the binomial testing that MaxScent does to see if any given model performs better than random chance. I finished up by making some maps. I used ArcGIS Pro again and imported the MaxScent graphical output into ArcGIS Pro and created maps, but I only did this for models with passing AUC scores. Then I concluded with an overlay map, which shows all warmest predicted areas, meaning areas with the highest predictions are all conglomerated into one map across all models. As for the results, my final sample size was 54 unique echolocations. The universal, environmental, and anthropogenic modus models were the ones that passed. All passing models had an identical and low omission error rate, but only the universal model performed better than the null via binomial testing. As for the percent contributions of predictor variables from the passing models, universal, the most informative predictor was slope, followed by land cover, then elevation. Minimal contributions from the rest. Environmental, first again was slope, but this time elevation and minimal contribution from the rest. And then anthropogenic modus. Modus picked up a lot of the slack there, followed by row density this time, and then minimal contribution from the rest of the layers. And here is the map of the universal model. So the results show that in a lot of the area of Kankakee Sands is predicted suitable, as well as some areas of Conrad Savannah, Nature Preserve, Beaver Lake Nature Preserve, Willisoo Fish and Wildlife Area, Iroquois County State Wildlife Area, some portions of the smaller habitat patches in the Northwest, as well as some agricultural fields surrounding these habitat patches. Slightly warmer predictions overall from the environmental model output. Next. And then much higher predictions overall for the anthropogenic modus model. But again, since these didn't pass the binomial testing, take these last two model results with a grain of salt. Next. And this is my overlay. You know, a lot of warmest predictions from that last model. But all models agree, a lot of Kankakee Sands and the other areas I outlined in the surrounding landscape are largely suitable. So specifically in terms of my passing models and their variables, slope was in the universal model. It was the most informative here, but the least informative throughout all the models in Hovick et al. 2015. This was kind of surprising, but like site selection is important relative to hen preference for sloped areas for nest site selection because it offers greater visibility. Land cover was the second most informative, and habitat is obviously important. Elevation, again, it's important because biologically, because lek sites are often elevated above the rest of the landscape because it promotes greater visibility and sound travel. Because these prairie chickens, these prairie grouse will boom with these sacs in their throat and make noise, and that's how they compete and do their leks. Again, minimal contribution from the rest of the layers. Environmental model, again, slope, elevation, minimal contribution from the rest. Next, please. My anthropogenic modus model. Modus was the only vegetative cover habitat variable, so it had to pick up a lot of slack when the others were excluded. Road density, again, slack taken up. And existing leks in the 4 states occur in a highly fragmented agricultural matrix. So it's not surprising that it at least had somewhat of a contribution in all of the models that passed. As for the limitations that I want to acknowledge behind species distribution modeling, it doesn't account for undetected leks or animals or input, doesn't account for mortality sources or effects of exotic species. So for exotic species, one that does affect the greater prairie chicken is the ring-necked pheasant. The females, the hens are nest parasites of the greater prairie chicken, and the cocks are like disruptors. So this introduced game bird does interfere with the reproduction of the greater prairie chicken. But even if these factors aren't accounted for in species distribution modeling, habitat loss is still the main driver of biodiversity loss. So I was satisfied with only evaluating habitat related factors. There was also some discussion in my committee about whether to include elevation or slope, because Kankakee Sands, if anyone has ever been there, it's really flat. There's not a lot of topographical variation. But since I was looking at all 5 states and extrapolating outwards in order to focus in on this one particular piece of the landscape, they would obviously become relevant over a multi-state area. So we decided to keep them. I did attempt to reduce spatial autocorrelation. I used 2 methods, Moran's eye correlograms and variograms. So I use multiple time step or distance step lags in order to obtain ultimately distances that were greater than 300 kilometers. And that's too large to preserve a meaningful sample size, which if I were to apply that, it would only leave me with 2 to 3 data points. So instead, I just use a spatial filter, like I mentioned earlier, 1.52 kilometers, which is the mid value of a range of observed distances between leks. That range was 1.33 to 1.71 kilometers. I believe my results are still valid, given that I attempted to account for spatial autocorrelation, along with Maxent's built-in resilience to spatial autocorrelation. And I applied my spatial filter. And also worth noting is that similar published studies did not mention spatial autocorrelation at all. And these were published in prominent journals like the Journal of Mammalogy and journals like Biological Conservation. Another thing I considered is if I were to, could you go back real quick?
Yeah. Sorry.
That's okay. One more thing I considered, if I were to do this whole project again, I'd probably leave out MODIS, because going from a 30-meter raster resolution to 232 meters is a lot of data lost. And I might have been able to account for spatial autocorrelation if I didn't size up all my data layers. Ready. So how do we interpret these results? Is it true occupancy probability? No, that's because we didn't use true absence data in our evaluations. Instead, we only looked at presence only data, and that results in a relative likelihood of occurrence. But it's okay. It's directly proportional to the true occupancy, so these relative likelihoods are still useful. Some miscellaneous points I wanted to talk about. More data points generally means better performing models. So I can only hope that, and I'm sure that biologists will continue to go out and collect these data points, and more data points will be created as more leks are created across the historic range. So for the greater prairie chicken, these lek sites are often collected. These data are often collected via roadside surveys, but leks are often not by roads. So there's a lot of potential for unaccounted for leks. Reintroduced greater prairie chicken may create leks in agricultural fields just before planting. Empty ag fields are open, And if they're surrounded by habitat patches that might provide these other relevant life history functions for the greater prairie chicken, such as brood rearing and nest sites, then they might go out and establish leks in empty ag fields before planting. So there might be some conflicts that will need to be resolved. And this has been observed in Illinois by my major professor. So it is a phenomenon that is known to occur. And the last miscellaneous point I want to talk about is that there's a major highway bisecting Kankakee Sands known as US 41. And that might inhibit some safe travel across the landscape, as well as add a potential source of mortality. Ready. Final conclusions. Only universal model performed better than the null and binomial testing. My warmest predictions in the universal model was in the majority of Kankakee Sands. Other areas were Beaver Lake Nature Preserve, Northern Interior Willow Sioux Fish and Wildlife Area, southern chunk of Iroquois County State Wildlife Area in Illinois, some agricultural fields, and some of the miscellaneous smaller habitat patches in the northwest area of the map that you all saw earlier. Final conclusions. Is Kankakee Sands suitable for greater prairie chicken reintroduction? My analyses say yes, at least in terms of macro habitat, meaning broad scale habitat classifications relative to lek site selection. And I want to thank my committee and the staff at the Nature Conservancy staff at Kankakee Sands for showing us around, giving us a lay of the land. One more. As well as the staff of the state natural heritage programs that lent me the data. And one final one. As well as the people I reached out to gather logistical and operational constraint information to provide for Nature Conservancy in order to inform any potential future reintroduction effort. Thank you.
All right, thank you very much, Zach. Again, if you have questions, let's please hold them to the end. And we will welcome our final speaker for this session, Jessica Elliott from Purdue University. Jessie is a master's degree candidate in forestry and natural resources at Purdue, investigating the use of remote sensing and particularly LiDAR to study forest structure and exotic invasion. Last year, she was named a 2020 Esri Development Center Student of the Year. Today, Jessie will be speaking on forest structural heterogeneity as a predictor of wildlife occupancy and richness. So let me get her presentation up here.
Hi, thank you so
And
much
we're
for
ready.
having Laura, and thank you so much for the introduction. I'm Jessie Elliott. My research focuses on determining whether it's feasible to use something like forest structure as a predictor of wildlife species occupancy, specifically in the state of Indiana. Next. Thank you so much. So I hope you'll humor me for a few moments, just in sort of a non-traditional exercise. So just kind of imagine you're a squirrel in the forest, could be an eastern gray like we see, or any kind of other species. And I'd like you to think about some of the habitat needs that you might have. So traditional studies tell us the importance of things like resources, competition with other species, nesting material or shelter, and maybe something like land cover in determining how suitable the habitat is for you as a species. And we can survey a site and count the number of mass trees. We can look at coarse woody debris, and even presence or absence of rival species. But what about the bones of the forest itself? Next. So ecologists have begun to explore the ties between wildlife and forest structure. It's still a relatively new field, but metrics such as tree height and canopy cover are being increasingly incorporated into habitat studies. So Recent studies have even incorporated the idea of maybe including structural diversity as a proxy for ecological niche space. However, many of these studies are site-specific. And anyone in wildlife who's had to do field data kind of knows that these are subject to human bias. Many of them are site-specific. And they incorporate field-based measures of structure that might be limited in spatial extent and limited by the accuracy of equipment. So remote sensing tools such as aerial LiDAR offer the opportunity to kind of quantitatively measure these forested habitat structures across large areas at very high spatial resolution. And so we can measure the complexity of these forests with aerial LiDAR. So we can look at the variety of height classes of trees, the number of gaps in the canopy or canopy openness, the different patterns of branching structures, and we can tie these back to the needs of specific species in ways that haven't been explored previously. So thinking back to your life as a squirrel in this hypothetical situation, would you have a preference for more open or closed canopies, right? Do you need a variety of trees in different heights, or would you prefer more uniform or homogeneous stands? So LiDAR allows us to map your home. Next slide, please. So just quick overview of LiDAR. I know Sun definitely covered this more in depth, but some of the data I use from remote sensing is aerial LiDAR, which stands for light detection and ranging. Essentially, an aircraft will have some sort of sensor on it that rapidly emits these pulses of light, and every time they hit a structure or something solid, they'll bounce back to the receiver. And so they generate these beautiful point clouds, which are kind of similar to a raster, except that in addition to an X and Y coordinate, they also have a Z component for height. And this allows us to look at things like topography, as well as things like forest structure. So the possibilities for using LiDAR are limitless. You can use it not only in the context of ecology, but certainly for more human-based studies as well. So this is kind of how LiDAR would see a forest as a point cloud. We have a tile down there where we have these beautiful kind of blue turquoise lowland areas that are maybe crop fields or hilly terrain. And then we have the kind of broccoli looking red orange patches that are forested land. Next. So in addition to LiDAR data, we also have camera trap data from across the state. So this is part of a larger project for the integrated deer management project. So this is something through Purdue. Essentially, there are about 800 camera traps set up across the entire state of Indiana, which have been manually tagged with over 2 million photos. So for each site, we have species information for that location due to the wonders of camera trap imagery. And as you can see, these are some of the photos we have from that. It's lovely to get to go through those. Next. So how do we combine the two, right? So we have this remote sensing data, and then we also have this wildlife species data. And so for approximately 300 forested plots across the state, it's kind of hard to discern all 300 because they are fairly clustered together. But for each of these sites, we have species data. So we know the presence or absence of certain species. And we can use that for things like occupancy modeling or for measuring species richness at these sites. And then for each of these sites, we used the camera trap as the center of the plot. We went ahead and clipped out LiDAR plots for each of these camera trap plots. So for each of these, we also have canopy structural information. So that includes something like average maximum tree height, which we're looking at, which in previous papers, this has been kind of used as not only like a proxy for measuring forest age, but additionally looking at the successional stage of a forest. We're also looking at vegetation area index, or VAI. So that's kind of just a measure of how much vegetation is intercepted by the pulses of LiDAR. kind of similar to LAI or leaf area index. We're also looking at gap fraction profile at each of these sites. So it's essentially the inverse of canopy cover. So how open are the canopies that we're looking at in these forests? We also looked at vertical heterogeneity, which is a measure of the variety in the Z dimension. So you could also see it as something like the variety of height classes in a forested plot. And also we're looking at top ergosity, which is a measure of the complexity of the outer surface of the forest canopy. And we also, these are somewhat preliminary, so we do intend on incorporating more metrics in the future. Next. So you can see for each of these plots, we not only have camera trap imagery, so I think that's somebody's dog that we managed to capture, which is not one of the species we look at, but it's always fun to have that as a nice little surprise. And then we also have LiDAR information for the surrounding plot. So we can visualize these plots in two different ways. Next. We also wanted to explore forest heterogeneity across spatial scales, simply because we are primarily looking at 7 different wildlife species. We have to acknowledge that these are species that have different natural histories. They have different home ranges. They utilize habitat at different spatial scales. And so we didn't want to just look at kind of a small scale plot, which is more traditional for field sampling. We wanted to explore larger areas. So we clipped radii anywhere from 25 meters all the way out to 200 meters to kind of see how these metrics were varying across stands or spatial scales. We ended up disregarding the 4th radii or radius size because as you increase the amount of land covered, unfortunately, you also increase standard error and the proportion of non-forested land. And we wanted to make sure that we were primarily looking at these little micro environments that exclusively contain forest. Next. So we went ahead and built occupancy models in program in R using the package unmarked. And we included all 5 of the structural covariates as or the structural metrics as covariates for predicting occupancy at a site. We also included year as a covariate to see if there is, a difference between some of the species we're seeing at sites between years. And for each of these 2 years that we had camera trap data for, we had a series of 14 days. And so that's essentially just a binary vector of presence absence for each of those sites, for each of those 7 species. And so we went ahead and ranked these occupancy models that we built using AIC values and determined which of these structural covariates is best predicting whether or not we see these species at a site. Next. So this is just, I know it's never fun to look at tables in presentations, so I'm going to maybe break this up a bit in the next few slides, but for each of these 7 main species, we found the best model covariates. And so a lot of these might not seem intuitive, but one of the wonderful things about looking at something like structure is sometimes it's not about the metric itself, but about what the metric stands for biologically. And so a lot of these structural metrics can be used as proxies for measuring other needs that a species might have in a habitat. For example, something like eastern cottontail that selects for more open areas with lower heights of vegetation that provide cover. You could use something like average max height for predicting the successional stage of that forest and kind of pinpointing areas that might be best suited for that species. So if you wouldn't mind going to the next slide. These are some of our camera trap images that I put in there just because they're great to look at. So yeah, first species we looked at was raccoon. So although he has, I think, arguably the most charming camera trap photos, he unfortunately, the best model for him was the knoll. which certainly makes sense considering what a generalist species they are, that they're not necessarily selecting for specific habitat features, but instead are present across multiple sites regardless of forest structure. Next. The next species we looked at was Eastern Cottontail. So for this one, the best predictor of species occupancy was average maximum canopy height, and with higher probability of cottontail occurrence in shorter forest stands, which is consistent with what we know from the literature. Next species we looked at was wild turkey. The best predictor for this was also max canopy height. And we know that turkey often select for forest gaps in order to have room for mating and for other life needs. So we're seeing turkeys select for, or not necessarily select for, but have a higher probability of occurring in taller forested stands. Next. For coyote, right now the best model incorporates canopy height as well as vertical heterogeneity. So we're seeing higher probability of coyote occurrence in shorter stands with a higher vertical heterogeneity, so more variety in height classes of trees, which shorter stands, so that can also be kind of a measure for how forested the area is. So we see shorter canopy heights in areas that have larger patches in them, because that brings down the average. And so because coyotes are edge predators and they utilize those larger patches, we can kind of see how something like canopy height might measure for that. Next. White-tailed deer, another species we suspected would be a generalist with the null model, but surprisingly, there were three covariates that worked in tandem to predict deer occupancy best. So for that, they selected for more canopy gaps, shorter forest, and plots with higher vegetation area. Next. For species like squirrel, I think this one to me was the most intuitive. We found that the best occupancy model used vertical heterogeneity as a predictor, which seems consistent considering that that's essentially a measure of the variety of height classes for trees. And so, the more variety we see in tree height, the more likely it is for us to observe at least one squirrel or member of the Sciuridae family in a site. And then for the last species, Virginia possum, we looked at. It's kind of hard to get a good picture of this guy, but it's still very photogenic. So the best model was top rugosity, and that's one we're going to explore further just because it's not very intuitive. And possums aren't necessarily a species that is closely tied to canopy complexity directly, but canopy complexity can also be a proxy for other ecological variables. And so these are essentially just preliminary results. And so the next step will be incorporating some sort of measure of land cover, something like NLCD data. We would also like to incorporate more detection covariates, because at the moment, our models do just assume a constant detection, but obviously that varies with something like time of day, weather conditions, or visibility in front of the camera. And so next step will be adding more covariates for our models, and then additionally testing not only which models are best relatively, but determining objectively how well these models are predicting presence of species. So a little bit of cross-validation and looking at AUC values similar to what Zach did. And so that's all I have for today. I guess the next slide is just kind of acknowledgements, because I work in two wonderful labs, and I'm so grateful to my lovely advisors and committee members, and then the wonderful, generous people at the Integrated Deer Management Project who were so kind in sharing their camera trap data with me. And then also just my lab mates who have been so wonderful. But yeah, I'd be happy to take questions during the Q&A, or if you'd like to DM me, I can give you my email if you have any questions or concerns, because that's also totally valid. So thank you so much for listening today.